Okay, hi everyone. I am Toby. I'm a senior software engineer at Westgate Software in Auckland. And I'm going to talk about composition. So please, if you have questions during the talk, feel free to put your hand up or just yell them out. I'll try to remember to repeat them for the video. Otherwise, we'll see if we've got time at the end for questions. So, composition. What I'm not going to talk about is anything to do with object orientation. I'm not going to talk about composition versus inheritance. What I'm talking about is when we have elements of some kind of set, and we have operations on those elements, and we get other elements of that same set. So, for example, let's take the set of integers, hopefully a set that we're mostly familiar with. We have operations on integers. For example, we have addition, multiplication, or whatever. You feed a couple of integers into addition, you get another integer out. So that's the kind of thing I'm talking about. And the kinds of things that I'm talking about applying composition to parts of our programs, for example, expressions, statements, functions, types, and the operations are things that, as programmers, we do to those things. So probably the simplest example is expressions. Our programs are full of expressions. I can't really avoid them. They're a very common thing to occur in all programming languages, but particularly C++. So in C++, we have a relatively small set of primitive expressions, and we can combine them together to make more complicated ones. So an example of a primary expression is a literal, 3. In an int literal, we can have string literals, float literals, user-defined literals. We can mention identifiers to get their value or to get reference to the object containing the variable. Lambdas are a kind of primary expression. Fold expressions, I just learned, are classed as primary expressions, which was something of a surprise to me. But anyway, this is basically the stuff that we make our expressions out of. These are expressions that we then combine together using various operations. So probably the simplest thing we can do to an expression is we can put it in parentheses. This gives us another expression. Has the same value, it only affects the precedence in the grammar. Probably an exception to that. There's probably exceptions to everything I'm saying, because this is C++, but I'm sort of giving a simplified overview. So we can apply unary operators to expressions. So a unary operator is an operation that takes one expression, gives us another expression. We can apply a binary operator, takes 2 expressions, gives us another expression. We can apply a ternary operator, which takes 3 expressions, gives us another expression. Function calls are kind of like an n-ary operator. So they take an expression that gives you a function or something that's callable as a function, and then some arbitrary number of other expressions, and that gives you a new expression, function call expression. So of course, you can't arbitrarily combine any expressions, because expressions have types and value categories and all kinds of other things, and there are lots of semantic restrictions on how you can combine expressions. But the interesting point, at least from my point of view, is that if the combination is valid, you get another expression. You don't get some other kind of thing. So expressions, pretty simple. Statements, they're also pretty simple. So we have a lot of statements in our programs as well. So there are several primitive statements, and there are ways that we can combine them. Probably the simplest, well, probably not the simplest. I think the simplest is probably the null statement, but a very simple kind of statement is the expression statement. So that's just an expression, any expression, with a semicolon on the end. That's an expression statement. We've got various jump statements, go-tos, returns, switch, no, not switch, break, continue, declaration statements. So then we can combine these statements together using various composition operators. So we can make a compound statement. We just take any number of statements, put some curly braces around them, and that's another statement. There are selection statements. So the if-else statement takes two statements, combines them together to make a statement. Switch is just takes one statement and gives us another statement at a very high level. So various iteration statements, they all just take one statement and return us a new statement, obviously with different semantics, but it's just a transformation from one statement to another. So I'm not telling you anything new, hopefully, assuming you know C++. So types exhibit the same structure. We have a whole lot of fundamental types, and this is not an exhaustive list. And then we combine them or modify them to form compound types. For example, we can turn a type into a reference to that type. We can turn a type into a pointer. We can turn a couple of types into a pointer to member. We can turn a type into an array. We can form a function type from an arbitrary number of types. We can form an enumeration type. We can form a class, so a struct or a class or a union. Again, takes some arbitrary number of types, gives us a new type. And that's basically what we have in C++ for composing types. So that is all stuff that the C++ grammar gives us. It's just syntactic rules, how you combine parts of programs. So things get a lot more interesting when we talk about functions. So when I talk about functions, I'm talking about anything that you can pass to the C++ 17 invoke function, function template. So that is basically something that invoke function in C++ 17 can take anything that meets the requirements of the callable named requirement. So that includes functions, although you can't pass an actual function, but references to functions, pointers to functions, objects with overloaded function call operator, objects with implicit conversion to function pointer, pointers to member functions, pointers to data members. So the first 5 in that list, these 5, are things that you can just apply the function call operator to. You can just call them with parentheses. These last 2 you can't write like that, but you can pretend that you can when you're calling the invoke function. We'll see an example of that in a second. So basically, when I say functions, I'm talking about callable things. And that includes functions, but also some other things. So here's an example, which will carry through a number of slides. We've got a struct representing a few bits of information about a person. We've got the date of birth and the name. We've got a function to take a date of birth and give you an age. So that's I'm not going to define that function. That's just, you can imagine it's just some kind of subtraction, work out how long ago the person was born. In a lot of ways, that's not a great function because it depends on what the current date is, but we'll use it as an example. So then the function we're defining is person age, so takes a person and returns the person's age. So just a quick note on the code that I'm going to show here. I'm assuming a using namespace std, just to keep the code short. So string here is a std string. Also, I've left off a lot of things that you would probably write if you were really writing this code. For example, I'm passing that person by value. There's not really any reason to do that in real code. You'd probably pass a const reference. So I've passed everything by value just to make it make the code shorter. So, can we see where there is a function composition? I won't make you answer because I've got the answer. But basically here we're calling date of birth to age, and we're passing it the result of getting the person's date of birth. So given our quite general definition of functions, there are two function calls there. We first call the DOB pointer to data member, and then we call DOB to age. So what I'm going to talk about now is how to bring that to the surface in the code. So I'm going to define an operation on functions called compose. So this bit of mathy looking thing here just says that we've got an operation compose, takes two functions f and g, returns you another function that takes one parameter, passes it to g, and then passes the result of that to f. And we can write that in C++. So this is function compose, takes two functions of arbitrary type, returns a new function that uses std invoke to first call g on x, on the x that you pass in, then calls f on the result of that. So that captures the pattern of function composition. So we had this code before, and then if we were to use our compose function here, we'd have this, which in this particular case, you could very well argue that that's not making things a lot simpler, and that's not really the purpose of this transformation. The purpose of this transformation is to call out the function composition that's happening in this code. So we're calling our compose function, passing it two functions. So this compose function is what's commonly called a higher order function. It's a function that operates on functions. That's one of the things that makes functions so much more interesting than expressions and statements, because you can't have an expression that operates on other expressions. The C++ grammar operates on expressions to compose them, whereas you can write a function that composes functions. So we're calling this compose function to return another function, and then we're just passing on our parameter that was passed into, our parameter here. We're just passing it on. So really this is, if you might be tempted, and I certainly was, to write this in this way, to say that the person age function is really just the value that's returned from that compose function. And you can write this, and this is, I believe, this is valid code, and then you can use person age as a function. However, I can't recommend that you do this because it doesn't work currently. It might work one day, but it doesn't work on Windows due to a limitation in the ABI. I think. At least that's my understanding. So I can't recommend that you do that. So yeah, you may well be thinking, we've just obfuscated our function here, but the purpose of making this transformation is to call out the fact that we're doing a function composition. And just to be clear, I'm not advocating that we all go and change our really simple functions that call two functions to look like this. This is for this is just a concrete way of visualizing in C++ how we can think about this kind of function. So let's look at a slightly more complicated example. So now we're going to take a vector of people, well, a vector of person objects, and we're going to figure out if there are any, we're going to use a possibly slightly flawed heuristic here to figure out if any of them are wise. So I'm sure that those of you who are well over 40 will realize the flaws in that in that heuristic. But the point is, what we're going to do is we're going to use the standard any of algorithm, which takes a predicate and a range, and figures out if there are any elements in that range that satisfy the predicate. I just realized this indentation is a bit messed up. It should be back there. So can we see any function composition happening in this code? So there's actually lots of function composition happening, because we've got standard any of, that's a function. We've got begin, it's a function. End is a function. But the composition that I'm talking about is this this lambda here, which might not immediately look like function composition. So there are actually two function calls happening there. One is obvious, it's person age, and the other function call is to the greater than operator. So let's see if we can bring that out to the surface in this code. So let's define a little higher order function here. So what this does is it takes a value and returns you a function that compares its argument against that value. So then we can rewrite our lambda to be a composition of greater than 40 with person age. So again, this doesn't necessarily read better in our code base, but the point is to call out the function composition that's happening there, and we could go further. We could call out the composition of any of with begin, end, and the result of compose. But you would get very diminishing returns, in my opinion. So we can then look at this greater than function and start focusing on that. So I'm going to introduce another operation we can do on functions, which is partial application. So this partial operation takes a function and a value for one of its parameters, and it returns another function that takes essentially one fewer parameters than the original function, and then applies the function to the parameter that you passed in and all the rest of the parameters. So C++ actually has this as a function built in the standard library. It's called bind. So we can rewrite our greater than higher order function in terms of operations on the functions that it contains. So we can use the handy standard function object called greater, which turns the greater than operator into a function, that we can pass around, and we can use standard bind to essentially say we're going to standard bind is going to return us a function that takes one parameter, and the one parameter is going to go here as the first argument of greater, and then we're going to bind this x that we passed in here as the second parameter of greater. So, have we improved this function? Well, actually, I'm curious. Does anybody think this is an improvement?
No.
All right, good. Yeah. Yeah, no, I don't think that's an improvement, but it does help to call out exactly what's going on there, because to me anyway, the before code there, it doesn't bring to the surface the mathematical operations that we're performing on our code. So I'm not saying you should write that code, but I think it's good to be able to think about that code. So we've got another even more complicated example. So we're going to sort a vector of people. We're going to sort it in place, so we can use the fabulous sort algorithm in the standard library. So we've got a function, we want to sort by age. So we pass sort a function, that lambda there, that takes two people, or I'll just say people. Takes two people and compares their ages. And then we want to sort by name as well. So we can write another function to sort by name. We call sort algorithm. We pass a lambda that pulls out the names and compares those. So inside those lambdas, we've got some kind of function composition again. But this is not quite the same as the previous kind of function composition. We've got two functions going on there. We've got the less than operator, and we've got the function that we're applying to both parameters. So it's a kind of a more complicated composition. So I'm going to call this composition operator on, and that's the couple of reasons. The main reason for that is that I'm familiar with this operation in other languages where it's called on, basically. It also reads reasonably well. So this is an operation that takes two functions, returns a function of an arbitrary number of parameters, applies the inner function to each of those parameters, and then passes them all on to the outer function. So we can write this in C++. It's actually relatively easy once we have the previous compose to base it on. So it's actually kind of similar. If you were actually going to write this function template on for production use, there'd be a lot more ampersands and standard forwards going on. But for our purposes, that's going to do the job. So then we can transform our sort functions into an explicit function composition. So the first one, sort by age, we're composing with our on higher order function the less operator with person age, and then sort by name we're composing less with person name. So just out of interest, does anybody think that this after code is an improvement on the before code? Yeah. We're getting a couple of little hands, and I think that the after code here has a number of really nice properties. One is these functions look more similar in the after case than they do in the before case, which makes it a little bit clearer that they're actually the same function, and we should probably factor that out. This it's shorter for one thing, and I think that actually reads quite nicely. It would read much more nicely if this on function was an infix operator, but that's a bit tricky to do. All right, so let's go and look at compose and on, which are these two major operations on functions that we've been talking about. And if we put them next to each other, you might notice that they're actually quite similar. And we can compare the C++ code corresponding to each of them, and it's almost identical. In fact, the only difference between compose and on is that on has a couple of dots in it. So that's actually something that's really cool about C++, because the fact that compose is actually just a special case of on just falls out from variadic templates and variadic parameter lists. All right. So yeah. So please do sing out if anything's unclear. So we can move on to a more complicated example. So what we're doing here is I'm going to make the date of birth optional. So this is the C++ 17 standard optional type. So the idea here is that maybe we don't know someone's date of birth. They haven't told us, or whatever. So we've got date of birth to age, which is the same as before. So now to calculate a person's age, we need to decide what to do if we don't know their date of birth. So what I've chosen here is to have person age return an optional age. So if we don't know the date of birth, we're going to return an empty optional. If we do know, we're going to return an optional calculated based on the date of birth that we know. So I factored out our heuristic for deciding whether an age makes someone wise, just to make things easier. So then we've got a function to decide whether a person is wise. So again, we have to decide what to do if we don't know the person's age. So what we do here, we calculate the person's age. If we didn't know what the age was, we're going to say, dunno, which is an empty optional. If we do know what the person's age is, then we can figure out if that age makes them wise. So just a quick note, by the way, this type is not something that I would recommend you have in your code base, because it, for example, an expression like this, it can easily get confused about whether you're talking about does the optional contain a Boolean, or is the contained Boolean true or false? So yeah, please don't use a type like this. Come up with something else. But for this example, it'll do. All right. So now we had our function before called any wise ones. So I've renamed it to any known wise ones, just to make clear what the semantics are. So this takes a vector of people, returns us a Boolean, and it's going to return us whether there are any people in the vector who we know to be wise. So in this lambda here, we're calling is person wise, which returns us an optional bool, and then we're just saying, we're using this value or member, which just says if the optional contains nothing, if it doesn't contain a Boolean, then we're going to use this value, which is false. So we're saying if we don't know if the person's wise, we'll assume they're not, because the point of the function is to return whether we know anybody's wise. You could do something different, but for this example, that's what we're doing. So do we notice anything about these two functions, which I could have put together to make more clear? But anyway, these two functions that deal with optionals are actually doing a very similar thing inside. They're checking to see does the optional have a value? If it doesn't, then I'm going to return an empty optional. If it does, then I'm going to apply some other function to the value contained in the optional and return that as an optional. So we can define composition operators for functions that deal with optional values. So this is the this is our previous compose operation, the higher order function that we had before, and then we can make a compose optional, which is yeah, there's a mess of code in there, but what it's doing is taking two functions, f and g as before, returning us a new function that takes one parameter x. So it's going to call g on x to give us an optional. If that contains nothing, we're returning an empty optional. If it returns something, we're going to call the function f on the value contained in the optional. And this trailing return type, decl type thing is just necessary to make it compile, because this null opt, it doesn't know what type of optional it is, so return type deduction doesn't work in that case. So then we can rewrite these two functions. We had person age and is person wise, which both had this pattern in. We can rewrite them to use this optional composition operator in the same way that we rewrote our function earlier to use compose, where we're composing these functions together and then we just immediately calling the result. So before, that was definitely a no, that's no good, don't do that response from everyone, I think. In this case, there's potentially some value because you're actually saving some code. You're potentially actually getting rid of a bug because I don't think I wrote any bugs in there before, but there's definitely scope for writing bugs there. So the next thing we can look at is this this lambda in any known wise ones, which is dreadfully sorry. There's meant to be a p here. Otherwise, that doesn't make a lot of sense. So we're determining if the person is wise, or maybe we don't know, and then if we don't know, we're turning it into false. So we can turn that into explicit function composition by pulling out this value or member function into a free function. And this is not just any old free function. This is a higher order function. So this value or function takes a default value, and then returns us a function that, when given an optional, will call value or on the optional. So then we can transform that code on the left into just a composition. We can compose value or false with is person wise, and that calls out the essence, at least mathematically, of what we're trying to do here. Again, you may find the code on the left clearer, and you may prefer that in your code base, but I think it's useful to be able to think about transforming it into the code on the right there, at least conceptually. So is this clear? Anybody want any clarification on this code? Because I've kind of just blasted through it a little bit. So who here is using optional in their code bases? Cool. Yeah. Half the room ish. Who here wants to be using optional in their code bases but isn't? Yeah, a few. Oh, I'd actually be quite interested to know why you don't want to, but it's probably not. I'm not meant to ask questions of you too much. But yeah, if you don't like the idea of optional, please come and tell me why not afterwards. All right, so the functions that I've been talking about so far have been very nicely behaved functions. They've been functions that take input parameters and they return results. And for the most part, they've been completely pure mathematical style functions where they're they're just going to return the same results if you give them the same inputs. And that makes for very easy composition. So the composition we've been doing, it's been really straightforward, and it composes nicely because we've got functions that take inputs and give us outputs. However, I don't know who here uses functions that say return bool for a success or failure, and then write their result into an output parameter. I've got plenty of functions like that in my code base that I work on. So these functions are, they're fine as far as they go, but they don't play very nicely with this idea of function composition. So here's an example. So this is like the simplest possible example. So we've got two functions, something that reads a string from a file, so it takes a path as input, writes an output, returns true if it succeeded or false if it didn't. We've got a parse person, which takes a string as input, has an output parameter of a person, returns true if the parse was successful, and we want to write a function to read a person from a file. So we can combine these two functions together. This is something like the code you'd write. You'd create an empty string, then you try to read the string from a file. If it failed, you return false, and if it succeeded, then you try to parse the person out of the string, and you return the result of that. So this kind of code is well, it's quite prevalent in the code base I work on a lot. I think it's pretty idiomatic in a lot of code bases. So what we can try to do is we can try to apply the same principles to bring the composition of those two functions to bring it to the surface, if you like, to call it out. So we can make a higher order function. I've called it compose out because it works with these particular sorts of functions that have output parameters. So we start with taking two parameters. Here we return a new function that has the correct kind of signature, as in it has an input parameter and it has an output parameter. So then we have to make a temporary object. And this is where it starts getting difficult. Like, what type should this be generically? It needs to be something that we can pass a reference of into G. So maybe it's like the type of the second parameter to G. So how to figure out what type of reference G accepts in its second parameter is left as an exercise for the reader, because it's actually quite nasty. You can do it in certain special cases, but I don't believe it to be possible in general. But anyway, assuming we can do that, we can call G to populate our temp. If it fails, we return false. Otherwise, we just call F with temp and write our output, and then we can write our composition like that, which is actually kind of okay, particularly if you've got more than two. If you had 3 or 4 or 5 or 10 things that you were trying to do, you could just list them out, and that would scale more nicely than the code on the left. However, there's a few nasty things about this. So one is, one that I already mentioned, is that we need a temporary of some type, but it's really hard to figure out what that type should be. So one option would be to make the user specify it. You can make it a template parameter to compose out. Another thing is that we need to default construct it. So that places a restriction on the type of on the kind of types that we can use in this scheme. And this compose out function that we've written, it's not really very general. It only works for functions that where the first parameter is an input parameter and the second parameter is an output parameter. And I know that the code that I work with, the output parameters tend to be sprinkled all over the place. Sometimes they're first, sometimes they're last, sometimes there's 1, sometimes there's 20. Not very often, thankfully, but sometimes. So you'd end up having to write a whole lot of different compose out functions. I don't, well, maybe somebody can. Actually, if somebody thinks they can write a general function composition operator that works on functions with arbitrary output parameters, then yeah, please let me know, but it's a pain. So anyway, the moral of the story is you can still think about this code on the left as function composition, but it becomes very difficult to actually write it as explicit function composition like this code on the right in any more complicated cases. All right, so any questions on functions? This is the end of the function section. Yes?
When you were trying to, you were talking about composing optionals. I see that as the maybe monad in Haskell. When you were talking about the function on, what is that and where does it come from? Which language did you take the name from?
So the question is that composition of optionals looks like the maybe monad from Haskell, yes. And then where does this on? I won't go back to it. So where does the on function come from? It comes from Haskell. Yeah. So Haskell has an on function very similar to the one that I defined. I'm not sure, I don't know if it's in the prelude, but it's a fairly common function. I'm not sure which module it's in. Yeah, you sprung me. Okay, so algorithms. Hopefully we're all thinking about algorithms now after Sean's talk this morning. So for you YouTube people, watch Sean's keynote first, which of course I'm sure you did. So so as an example, let's say we're going to stick with our wise people example. What we want to do is we've got a vector of people. We want the names of the wise people. We're not interested in their ages or any other attributes of them. We just want to know the names. Maybe we want to do some sort of statistical analysis on what kind of names wise people have versus non-wise people or something. I don't know. Okay, so we've got a function, names of wise ones takes a vector of people. This is the sort of very straightforward code that I think, well, that I would probably write. In fact, I did write this. Funnily enough. So what we do, we're going to take a vector of person, and the output is a vector of string. So we just loop over the people. We check, is the person wise? Defaulting to false if we don't know. If they are, then we're going to push their name into the names, and we just return the names. So is that pretty clear? Yeah. Okay. But I said algorithms, and I didn't use any algorithms. Well, I mean, I did. I wrote an algorithm, but I didn't call any of the standard algorithms. I didn't write a function that's an algorithm. So there's a couple of standard algorithms which seem like they're probably applicable to this. So there's copyIf, which copies from one range into another the elements that satisfy a predicate. And there's an algorithm called transform, which copies from one range into another elements transformed by some unary function. So we can rewrite this names of wise ones function to use these two algorithms. So first of all, we copy into a new vector all the people that are wise, and then we can copy or transform into a result vector the names of those people. So that's great, right? We've reused standard algorithms, and we've got nice, understandable code because we don't have to try to decipher what the loop is doing. But yeah, we've got a whole extra vector here, which we've allocated and copied people into, which is not ideal. So in the best case, that doesn't matter. Maybe these things are small. Maybe people are cheap to copy. Maybe our system just is not performance critical or memory constrained at all, in which case this is probably fine. So there's a few other things we could do. Anybody have any suggestions for what we could do to try to improve that? So I had a couple. One is we're already taking a copy here. We could just mutate this in place. So we could do a remove if to shuffle this copy down, and that doesn't really help us because we actually don't really want to make this copy at all in the first place. Ideally, we wouldn't pass this by value because this function doesn't really need a copy of the vector. It just needs to inspect it and create a new vector with the results. Another thing we could do is we could make this this copy if the output iterator that we're passing in there. We could make some sort of fancy transforming iterator that takes people and outputs, writes into the destination vector strings. And those things exist. They exist in Boost, and they're really useful. But then we're not composing these standard algorithms. We're essentially using copy if and some other iterator thing. So my conclusion for this is that for this kind of code, when you're copying from one thing to another, the standard algorithms just don't compose very nicely. I know that might be considered heresy, perhaps, but for a lot of things they do. I don't mean to bag the standard algorithms or the STL. Certainly not after this morning's history lesson. But for this kind of thing where we've got an input and we want to return a result, and we want to do multiple operations to compute that result, they're not ideal. So if you were in the previous talk by Chris just before, you probably know what I'm talking about. But otherwise, I'll try to explain briefly. So this code is something that you can write under a couple of conditions, and this is at least in my opinion a much nicer way of writing that function. So in this code, we only create the result vector. We don't create any intermediate data structures, and it's short. And I think it quite succinctly expresses what it is we're trying to do. So what we're using is these things, filter and transform here in the view namespace. These are range adapters essentially from the range v3 library. They are proposed for standardization in C++. So what filter is doing there is it's taking as its parameter a predicate, and it's returning an object which can be chained with the bitwise OR, aka pipe operator. C++ is kind of known for misusing bitwise operators for non-bitwise things, so we're So we're probably okay with this. If we're okay with I/O streams, right? So what this is saying is we're creating a filter range adapter here that then gets people piped into it, as in passed as a parameter, essentially is what happens. So what that does, that people pipe into view filter, gives us a lazily evaluated view. So the lazily evaluated view doesn't actually do anything until you ask for elements. When you ask for elements from it, by iterating over it, so a view is something that can be iterated. It's got a begin and an end, which give you iterators. As you iterate over it, it tests each element from the source range, which is people in this case, to see whether it satisfies the predicate. If it doesn't, then it skips on to the next one and keeps skipping until it finds one that does satisfy it. And then we've chained on the transform view adapter, which takes a function, which is what we want to do with the transform, and it takes elements from its input range, which in this case is the results of the filter, applies the transformation function as you ask for elements. So everything after the equals sign essentially does nothing. It just creates a view object that, when iterated over, will perform the filtering and transformation. So then I'm assigning, well, I'm not assigning, I am initializing a vector with that view, and that is something that is proposed separately, as I found out. I think is that correct, Chris?
How do you mean?
The initialization of a vector from a range, that's a separate. Is that
range v3 can do that?
Yeah.
With the range adapters in standard, it's a bit different.
Yeah. So this code might be correct in range v3, but not correct because none of this stuff is actually finalized for the standard yet. So yeah, if you want to use the range v3 library, you can write code like this now. I've got to say I haven't tested this code, but something like this will work. So range v3 is requires quite a conforming C++11 compiler, which unfortunately, as far as I know, means a very, very recent version of MSVC if you're using the Microsoft toolchain. And even then, I'm not entirely sure whether it works. But this stuff is proposed for C++20. So if you want to go and read the proposals from the latest mailing, you can. But there are three that I did a quick skim over because the mailings come out relatively recently. So this was added in quite last minute. But the three that I think are relevant for this, there's the one ranges proposal, which lays the groundwork for ranges, puts a whole lot of concepts in place, and gives you range versions of standard algorithms. There's range adapters and utilities, which gives you the view filter and the view transform, which I've used, and a few other useful things. And then there was another proposal which I saw in the mailing, which I was hoping was going to give me the way of initializing a vector from that, but yeah, don't quote.
As it does do the other thing.
Oh yes. The question was, I'm right. Right. So any questions on that stuff before we wrap up? Yes.
There is also P1035, which adds a few more range adapters to, or hopes to add a few more range adapters to C++20.
Okay. So the comment was I forgot the number already.
1035.
P1035 adds some more range adapters. Yeah. It's another proposal which you might be interested in. Talk to Chris. Yes.
Do you use the boost range library, and do you have sort of any comments on what's been improved
Yeah, so the question is about the boost range library and how that differs from what's in range v3 and what's been proposed. So I'm not really familiar with the boost range library. It has a lot of similarities. The naming is slightly different, and so my understanding is that it has more issues with lifetimes of temporaries and things, but it's much the same thing. It's the same idea. Yeah, I can't really say much more than that. Cool. All right. So to wrap up, and then I'll ask for more questions afterwards. So what I'm hoping that you will take away from this talk is that composition, in the sort of general sense that I've been using, is everywhere. We use it when we write our programs. We compose expressions together to make more complicated expressions. We compose statements together to make function bodies, and we do it all the time when we're programming. This composition, a lot of the time, is hidden or implicit. It's under the surface, and that's fine. I'm not saying that's bad, but what I'm saying is that we can make it explicit. If not in our code, then in our minds, and that helps us to think about the code. Function composition is quite interesting because we can write functions that compose functions, functions that create functions. I find these higher order functions fascinating, kind of awkward to work with in C++, but still worthwhile. Output parameters, pretend that's spelled correctly, not so great for composability. Personally, I think they should be avoided. They can't always be avoided. I mean, there are really good reasons sometimes to use output parameters, and I'm not saying don't use them, but if you want to make your composition more explicit, then you probably want to avoid them. The standard algorithms don't compose well in some cases. As I said, they compose really well in a lot of cases, and those cases are generally when you're making modifications in place to some range. But for functions that just take an input and then don't change it but return an output, they don't compose that well. But the good news is that ranges and range adapters and the various things around that are being proposed for C++20 will largely fix that. And we'll be able to write nicely compositional code that combines standard algorithms. But yeah, most importantly, think compositionally. All right, well, thank you very much. If there are any questions, we'll try to do this microphone thing, so if you can ask it into the microphone.
Thanks. So one thing you didn't talk about were how ranges introduce projections, and how do you feel they play into composability?
Yeah, so projections are kind of cool. So the rangified algorithms like sort and things, the range version takes a single range object rather than a pair of iterators, and a lot of them also have an extra parameter called the projection, which is another function which is applied to the elements before the main operation is applied. So for example, the sorting examples that I gave would be much simpler with the range sort algorithm, if I understand correctly, because you can pass your comparator, the binary function that implement less as one parameter, and you can pass the other function as the projection parameter. So they essentially have the on operator built in. Is my understanding. Does that gel with your understanding of how they work? Yeah. So that'll make the kind of code that I was writing with on much simpler to write, and you don't need to write on explicitly for those. Yeah. Whether that's better or worse, I mean, yeah, it's probably better. All right. Any other questions? Okay. Thank you very much.